Hi everyone, and welcome to our talk, Reinventing a Character Creation Pipeline Using Landmarking, Simulation, and Shared Character Data. My name is Ferris Webby, and I was the rigging supervisor at Blue Sky Studios when the studio started to think about how a character asset creation pipeline could be made more efficient for our future films. In this talk, you'll hear from some of the wonderful artists at Blue Sky who helped imagine and contribute to this project. Each artist here and many others throughout the studio were vital in realizing our end goal of producing characters faster while keeping quality, aesthetic, and creative flexibility intact. So why did we want to do this? It's obviously a large task requiring many components and interlocking pieces. Well, we had a few general needs to make our current pipeline more efficient and effective. First, we wanted to create assets faster. We also wanted to work more organically together as a team. And finally, we wanted to share and reuse as much work as possible. The basic philosophy around all of these needs was to add more visual context and fidelity to an asset in its early developmental phases. The more we could do this, the more time we save in production, and the better the pipeline can become. It's for these reasons we decided to rethink how we created characters at Blue Sky. This outlook was based around a few goals. First of all, we wanted to have early integration of disciplines. With that, we wanted faster iteration between the disciplines. We wanted an ease of use for tools and workflows across disciplines. We wanted to have scalable and shareable data. We wanted to proceduralize or simulate data wherever possible. But we also wanted to focus on the creative. Some of the main components we developed for this pipeline included something called the Unimesh, which was our universal topology and the philosophies that went along with it, the Morph Skeleton, something called the puppet rig, and the character data. All of these will be covered within this talk, and each contributes its own form of efficiency for the pipeline. And here you can see a simplified view of the early development pipeline. And it shows how these components interact with the involved disciplines. Because we are offering a workable rig from the Morph Skeleton so early in the development timeline, other disciplines can be provided better fidelity for early tests, including tests for proportionality, especially when in poses, garment fitting and draping, and early fur and material viz dev. These tests can happen even before rigging creates any official publish, which helps make this pipeline work in an extremely organic way. The puppet rig and the character data further increases fidelity of the asset over time and helps us reuse the data for future assets. Another advantage to this approach is the ability to review assets early and often with directors, with much more clarity of context, so issues can be addressed quickly. With these goals in mind, we set out to develop the core of the system, the one component all others would be developed around. We wanted to take some focused time to implement a solid universal mesh. Dubbed the Unimesh, this model would have rules and philosophies that would keep the mesh easy to use, modify, or upgrade if necessary.
Hey everyone, this is the Unimesh portion of our discussion. My name is Christian Hanishevsky. I was a character artist at Blue Sky Studios where I mainly focused on modeling and rigging.
And I'm Chris Pagoria. I was also a character artist at Blue Sky Studios, specializing in modeling and rigging.
So the universal topo, right? We were using it before on background characters. We never had a concrete universal topo throughout our entire pipeline, and we were using it for background characters, removing the arguments around kind of creating the shape with the rig, and that just created a really messy mesh that we kind of pushed down the pipe. But we wanted something from scratch, right? So our approach was less is more. We wanted enough topology to hit major forms and then have the mesh adaptable after the first initial transfer. So what that means, after the first initial rig transfer, we were able to go in there, remove spans, add spans, change the topology without being so destructive to the rig. And the key thing here is we wanted it to be light and easy to work with. So when we were designing the universal mesh, we wanted something that was specific but also generic, not something that was really, really crazy. So we designed this as a universal mesh. Also in Maya, the way we designed the workflow was we had the landmarks as selection sets. When we were using Gozi to go from Maya into ZBrush, those selection sets would end up becoming polygroups, and then modelers were able to view those things when they were putting those characters in pose and also hit a lot of the tech notes early on. We also had a lot of documentation, and we were showing this to other departments. These were some of our major focuses, areas of high deformation and joint placement, those red areas where you would place the joints in between, where you could see like the arm, shoulder, spine, hip, leg. We also have halfway points between areas of high deformation, such as the biceps, forearms, thighs, calves, and that's where you'd put the joints, to have, bend joints. We wanted to mark center of mass from the front and back view, and these are these gray landmarks, and that was just to see, how wobbly that mesh would be, and this would also to help the rig transfer for the universal mesh and making sure that, those joints being placed based on those landmarks would be absolutely straight. And in this image, you can see, how we're placing those arguments in the hand. Also, some of the things that would be showing to the modeling department, the lengths of the limbs. And in the face, some things such as, keeping the vertical spans and the brows absolutely straight between all the characters, having the same behavior between the eyes, and also keeping the spans and lips absolutely straight. And one thing that we designed the universal mesh to do was that if we added some spans into the face, it would travel within the neck and head area but never go into the body and kind of destroy the body topology. Another key thing here was the facial features and how they were lining up. One example is like the top of the ear and the pupil, making sure that behavior kind of transferred over between all the characters. And again, using the same type of idea of having the behavior the same, like for the nasolabial fold, having those spans kind of behave the same, that same kind of arc, no matter what form it is. And we also wanted to emphasize, the actual, again, the behavior of the spans, if they were convex or concave. If they are concave on the universal mesh, they should be also concave in form on the new shape with the new transfer to make sure that those blend shapes would transfer over nicely.
Cool. So as Christian mentioned, landmarking is super important. So this is a good example of a character that has a completely different design, it has a completely different proportions, but the landmarks are all similar. So it's really important to have proper spacing to make sure your transfer is the best it can be. So this right here was a good test case we did. So this was modeled by lead modeler Sean Cusick. This is an alternate design for Killian in Spies in Disguise that we were able to repurpose. So this gave us a lot of really cool challenges. So the mesh is more specific than our topology allowed us, and also the scar is asymmetrical, so it allowed us to test a lot of really cool stuff. So if you look here, the one on the left is our universal topo, and then the one on the right is a subdivided mesh with some custom cutting. So we need to figure out a way to get the information from the universal topo to the higher res mesh. So after a bunch of different things that we tried, we ended up using a really simple but powerful script called transfer deformers that we developed. So transfer deformers is a tool that transfers your skin cluster, your blend shape, your lattice, really any deformer from your rig to another piece of geo. So this is really powerful in that you could grab pieces of your mesh and transfer it. If you want to start over in an area, you could start over in like the smile and get those shapes back from your previous mesh. It was really flexible and really powerful. So if you look here, this is that new mesh with everything landmarked properly. So even though the form is drastically different, we're able to still maintain the landmarks and get a nice transfer. Cool, thanks for watching.
Hello, my name is Daniel Lima. I was a senior character TD at Blue Sky Studios for almost 11 years. Last year, I jumped into the game industry as a senior technical artist working at Undead Labs. Today, I'll be talking about Morph Skeleton. What is Morph Skeleton? It is a unique skeleton connected to the mesh, which retrofits the character rig to any new character model applied as blend shape targets. It is the foundation of the character rig in our pipeline. It is a rig done once to retrofit all other characters within the same skeleton structure. It is a modular system capable of building any morph skeleton to adapt any skeleton type. It was designed to install inside a universal mesh using specific landmarks for joint position. This approach gave us the best relative joint position to receive the formation data to any new character. The morph skeleton is generated by a modular rig system that creates three types of components: coplanar rig, collinear rig, and unit rig. The components of the morph skeleton are driven by rivets on faces bound to the mesh using a wrap deformer. These blue faces with rivets is what we call anchor faces. The anchor faces are generated by using morph skeleton modules selecting 4 vertices of the character's geometry, paying attention to the landmarks. The anchor faces have an UV control representing the face area. which can be tweaked after the morph skeleton is used. In this example, we can see the UV control being used for demonstration in one direction. The coplanar rig represents sections of the character skeleton, which will need an IK system such as arm and legs. It contains 3 independent controls to connect at the base, hinge, and tip of a limb. The arrow at the corner represents the direction of the hinge and the plane which all joints are virtually bound to. The collinear rig represents sections of the character's skeleton, which is a chain of joints, such as spine, neck, fingers, and tails. It contains 2 main independent controls, which keeps the collinearity of the chain when moved. It also has X number of micro-independent controls in between, which can also be freely moved. The orientation of its joints is correctly maintained for a clean character rig installation. The unit rig is an independent joint with internal properties such as look at, word, and surface tangent orientation. It has only one control, and it is programmable to point to another transform, dynamically copy the orientation of different joint, or leave it locally to the orientation of the ankle face. Each morph skeleton component needs to be assigned to the original section of the character skeleton. The class provides ways to quickly do this by selecting the joints in order before running the command. In this example, we can see the assignment of the joints to the morph skeleton component. At the attribute editor, we can see the actual joints that are actually part of the morph skeleton rig. I will be able to select the joints of the actual skeleton in this order, select the tip mover of the morph skeleton collinear rig, and run the command assign depth joints. We can see this again, and there we can see the assignment of the joints of the morph skeleton components. The benefits of using morph skeleton are key to our pipeline. Once the character skeleton is retrofitted to a new volume, it's done precisely to its joint position and orientation, giving us a much better usage of any deformation data such as skin weights, blend shapes, and any deformer weights. With the help of universal topology and the character data, allow modeling, animation, and simulation department build fully functional rigs in less than a few minutes to test away.
Hello, my name is Todd Hill, and I'll be talking about the character data system. So what is the character data system? It was using the universal topology. We plan to collect and transfer data between assets. The collected data will grow over time, allowing us to create a library of different data that we could then use on different designs. The sharing of data across different topologies with a master volume, so we could even at some point have a volume that we can then use to transfer between topologies. Examples of the data that we started with were blend shape data, skin cluster data, control rig data, control rig settings. We could do really any data that we can export from the rig. And then we built a UI called the Rig Builder for streamlining the process between departments. So why the Rig Builder tool? Like I said, it's a one-stop shop for anyone in the character department to rapidly build in a quick asset. It gives modelers a quick way to pose the character, gives costumes and tailoring a quick way to check the fit, gives the animators a quick way to test proportions, gives riggers a quick first pass, and within minutes you can use it for any other testing purposes that the pipeline may need. So here's an example of the Rig Builder tool. Right now I am loading an asset. So this is just the model, and then I am going to, these are the different tabs we could apply data for. I'm going to run the Morph Skeleton that Daniel talked about before to auto fit to the model. I'm going to go in and adjust the Morph Skeleton a little bit based on some planes that the model didn't quite hit. And then I'm going to update the Morph Skeleton, which snaps all the joints to the finalized locations, arguments. Those are some different install options that we have. Now I'm going to install a rig, and boom, we have a rig. And that's the area where I can choose the data I want to apply, which is a skin cluster. As you can see, there's also blend shape data in there and other data. And then this allows the modeler or whoever to transfer the deformation to the clothing. We have two modes. One is an in-house transfer that we developed, and the other is just a wrap. And you can see how quickly we can create an asset to put it out for other departments, or even allow other departments to create their own assets. And that is the character data system. Thank you.
Hi, my name is Brian Anderson. Before I get started, I just want to say thanks to our head of character, Sabina Heller, and the team for believing in this proposal long before there were any results to share. Thanks. So I worked on developing a simulation-based workflow for character deformation. By utilizing simulation, we hope to gain the physicality of simulated results in terms of fall-off, volume preservation, and deform surface quality, but also in the consistency of those results over isolated and full-body poses. Our end goal was to create a deformation data set that we could use to harvest shape corrections or pair with machine learning to get the most out of the deformation system. Utilizing Ziva Dynamics for its excellent elastic solver and toolset, I took a stop-motion approach to the simulation build, starting with a simple armature that could easily be bound to our existing rig. From there, tissues were modeled to fit our unimesh, split in key areas that let us control volume, dispersion, and TED mesh resolution to help achieve the look we wanted throughout the simulation. Notice that the armature and bones poke through the outer surface around the elbows and knees. This allowed us to sculpt by hand in areas where we wanted finer control. Here we see the resulting simulation going through a typical range of motion animation test. Simulation settings were adjusted to work with some of the more extreme poses, and dynamic secondary motion effects were turned off. We can see the effect of the tissue separations used in this technique. Each section maintains volume buildup within its bounds. This accentuates squash and stretch as tissues push against their neighbors by helping keep the effect localized to the deforming area. The simplified setup has just 7 tissues, 18 bones, and roughly 40 attachments. We took advantage of Ziva's layered material workflow to help direct folds and collisions by adding 2 or 3 material layers per tissue. Simulation times averaged between 4 and 15 seconds per frame, maxing out at around 40 seconds depending on substeps. Here we see a comparison starting from the left. We have a typical skin cluster blend shape workflow. In the middle are the Ziva tissues, and on the right we have our simulation result, where our final mesh is bound directly to the tissue objects with no other connection to the skeleton. If we stop here, for instance, we see an undesirable deformation, which is the result of a lack of a combination shape between the left and right legs. In our simulation result, we have a clean shape in a complex area. Here again, we have a complex pose involving both legs in different angles with twisting. This pose not only becomes cleaner in the sim, but also regains its structure and form in a way that we would expect. Although these are the type of results that are typical throughout the simulation, there are places where we see the handmade result is better, which is expected. Our goal is to set a base level of clean deformation for artists to work on top of. In this example, we've used the Unimesh and Morph Skeleton to warp the shape of the tissues to fit a new body type and retarget our rigged bones. The Ziva simulation is loaded and adjusted to fit this larger, more difficult use case. After binding our model to the Ziva tissue objects, we get the type of deformation we would expect to see through a range of motion that's not defined by specific targets at specific angles. The creation of this deformation dataset gives us a resource that can be used in many ways. As many or as few shapes as needed can be extracted to PSD, and if motion range is changed during animation, we can go back and take new poses to fill any gaps. Extracting shapes and adding them into our rig system worked really well because of the consistency. All the shapes came from the same physically based system, so no matter what pose we're in, the fold lines, the volume buildup were all the same through each extracted shape. So the features lined up and transitions through the poses held up very well, even in a basic driver-driven blend shape system. This can be difficult as an artist where each shape is sculpted by hand, and tracking those features and changes over multiple poses in a motion range is tedious and difficult. If we add in machine learning, we can take full advantage of the deformation set, getting more pose shape data than we could ever by hand. By using simulation as a starting point, we gain an excellent high-quality base set of deformations and allow character artists to spend more time on art direction and less time fixing poor deformations. Using simulation-based tools for deformation offer interesting potential benefits. Clean, uniform quad geometry while deforming, consistent results through complex poses, very nice shifting volume transitions between poses, smooth silhouettes by bypassing typical muscle-based system sliding effects and microforms with a simple stop-motion approach. Topology is less important since the binding of our model to the tissues is not complicated. We can change the topo at any time. With a more complete base set of deformations, the overall quality is higher. In addition, artists can spend more time on art direction. By utilizing the deformation dataset, we can go back to that set at any time for more shapes or adjustments to the deformation system as a whole.
Thank you for joining us for our talk today. I hope we've sparked some thoughts and ideas you can all implement in your own pipelines to help your teams work more organically and faster together. Special thanks to those listed here who were extremely crucial to the creation of this pipeline, and to the amazing team of artists at Blue Sky Studios. Have a wonderful conference.